important, and how workflows can be designed using this MBNpy package that we are developing. So I will.
Because I think it's mine, but you'll want to bring them. Sorry, maybe our battery issues, but try to see if it should work now.
Okay. So yeah, I'll first start from the general background of this research that the motivation is based on the scale and the complexity of real world systems. So for instance, this figure shows the UK rail network, which consists of hundreds of stations and thousands of miles of rail tracks. And what we observe is all these local incidents with these uncertainties. And now the question is how all these uncertainties are combined together to decide the uncertainty at the system level. So this will be the question that, sorry, that is my bad, but you can just put it down on the floor. Yeah.
Thank you for
You can just put it on the floor. It's right. They're turned back. So and this will be the question that I will illustrate today. So and especially we are developing this package that that somehow facilitates the methods that we are developing, and we are also actively looking for collaborators to co-develop this line of methods. So first, I'll explain how this matrix-based Bayesian network can help handling large-scale systems as an alternative data structure to Bayesian network. And second is how we can use this very recent algorithm called branch and bound reliability analysis of coherent systems, BRC algorithm, that we can automatically handle all these large-scale systems. So I'll first briefly explain the Bayesian network. I think many of you are familiar with this concept, where it is a type of probabilistic graphical models that whose visualization helps modeling complex probabilistic models. And in Bayesian network, random variables are represented by these circular nodes, and the directional dependence between these variables are represented by directed edges. A useful fact here is that causal relationship is a subset of directional dependence, so we can decide these edges based on causal understanding of the real world between real world variables. And given a graph, it is once we specify the graph, then it is straightforward to formulate the joint probability distribution. So here, each node is quantified by a distribution conditioned on their parent nodes. So in this case, Px doesn't have any parent node, so Px is defined as a marginal distribution, while Y, which has X as its parent node, then it has this conditional distribution being conditioned on X, and the joint distribution simply becomes the product of all node distributions. So we have these two nodes. So we have two conditional distributions, and the joint distribution represented by this Bayesian network over the variables in the graph is simply the product of all these distributions. Then now the problem comes with system reliability, where we want to quantify the system event within the Bayesian network. Then because system event always depends on the component events, so we cannot avoid this converging structure between components and the system event. In which case, we need to quantify this conditional probability. And when we think about the combinations that we need to compute and store, exponentially increases with the number of components. And now the rest of the presentation will show how this complexity has been addressed using this MBNpy methods and BRC algorithm. So matrix-based Bayesian network has been proposed as an alternative data structure to store this system events conditional distribution. So for instance, if we have these three variables and we have this conditional probability of x3 as in this relationship where x2, if x takes the value of 0, then x1 takes a value of 1 with the probability 1 and etc. That in the conventional approach, usually we store these probability distributions using table-based representation, where we store only the probabilities and the associated states are inferred by the locations of the cells. And in other words, it is inevitable to store all these probabilities. And on the other hand, in case of matrix-based Bayesian network, now we use matrices instead of table, and we call it conditional probability matrix CPM. And it contains two matrices, event matrix and the probability matrix. So event matrix, in each row, we define which event it is, and on the probability, on the probability vector in the same row, we specify the corresponding probability. And in this way, we can be more flexible about what we store. So, so to explain how we can achieve that flexible storage with this data structure is first, we introduce this new state called the composite state that can represent the multiple states at once so that we can encode the patterns in a system event. So for instance, in this case, we see this relationship where if x takes a value of 0, then regardless of state of the other component, the x1 takes a value of 1 with probability 1. And for this, we introduce a new state for x3, 2, which can represent both 0 and 1. Then we say if x2 takes a value of 0, then if x3 takes a value of 2, then x1 takes a value of 1 with probability 1. And another advantage is that we don't have to include these 0 instance events, which are prevalent when we are dealing with deterministic system events, and this can also further reduce the memory. And also, when we are dealing with this approximate inference, then we include only the subset of events that we are going to use for the inference. So this so that this matrix format can be contained, and the same algorithm can apply when we are doing approximate inference, such as deterministic bounding or sampling. So this is the basic idea. So, and we developed this package that is called MBNpy. So you can pip install it, and in MBNpy we use two variable types, so CPM and variable. So first, in variable, we store the information of variables. So here, and you need to provide two pieces of information, name and the values. So for name, we can store the name that we are of the variables, and in the values, we specify for each state what meaning is referred to. So for instance, in this case, it is storing that state 0 means failure and state 1 survival. And this is just for reference sake for the users to remind of what each state means. But also this means that this variable has two values, 0 and 1, and the reason that it starts from 0 is because Python is based on zero-based index. Then now with these variables defined, then we can now construct the CPM where if we want to quantify this distribution, then we have these three variables in order, and these represent these 4 rows that we have, and the corresponding 4 probabilities. And the number of child is 1 because x1 is the only child here where x2 and x3 are the parameters. And if we define this, and if we print out the table, then we can check that it was correctly encoded. Then how does this the first example that we can save the memory is this series system where we have these 4 components. And now if we want to quantify this conditional distribution, then we use this information that if one component fails, then the system fails regardless of the other components. But there's only one constraint that when we construct this CPM, that the events that are represented by the rows should not have this intersection events. And this is because if there is a duplicated event in a CPM, then we would end up double counting some events. So in order to ensure this, branch and bound or decomposition is often helpful. So for instance, this shows the decomposition for series system, where here we know that if x1 fails, then the system fails regardless of the state of the other components. Otherwise, it simply survives, but x2 fails, then the system fails. And we go on until we end up with, we reach this last branch where all components survive, so the system survives. And in terms of the CPM, then each branch becomes a row. So here, if x1 takes a value of 0, then again, we are introducing this composite state where if x2, x3, x4 can take any value, and the system will fail. And if otherwise, if x1 survives and x2 fails, then x3 and x4 states doesn't matter, and the system will fail, which represents the second branch. And we have this last branch where all components survive and the system survives. And because we are dealing with a deterministic system, we have all probabilities as well. And now we have brought down this complexity from exponential to the linear one, which is significant. And this is also because series system is a relatively simple definition. Then if we go a little general, then this shows the network connectivity, where we are interested in the connectivity between N1 and N4, and there are 5 component events that represent the state of each of these 5 edges. And in this case, we can start from a decomposition where we start from the total event space. Then first we start from some random choice x1. Then if x1 fails, then x2 and then if x2 fails, then the system fails regardless of the other component states. And we found this minimal failure rule, which is if x1 and x2 fail together, then the system fails. And if you look at x5, then if x2 and x5 survive together, then we found this minimal condition where x2 and x5 survive together, then the system survives, and we can conclude that this branch belongs to the survivor domain. And we can go on, and we can continue finding these new rules and new failure and survival rules, and we terminate the branch, the decomposition when we are done with when we identify enough branches of the system domain. Then now, originally there are a total of 2 to the power of 5, so 32 instances, but we could bring down this to 10 branches. And we have found these 4 minimal survival rules and 4 minimal failure rules. So, and if we want to construct this CPM, then for instance, in this case, if x1 and x2 fail together, then the system fails. And if we look at the second one, then if x1 takes a value of 0 and x2 takes a value of 1, and x5 takes a value of 0, and x3 takes a value of 0, then S fails, And in this second branch, there is no X4 specified. So now we leave this state of X4 as 2, and we can continue this to help to construct this event matrix with 10 rows. Then once we are done with this quantification, so all this effort is to decide this probability distribution of this S. Then we can specify the probability distributions of the other components, where, for instance, if x1 and x2 takes the value of 0 with 1% and 1 with 99%, and x3 and x4 if they have value probability of 5%, and for x5 if they have the value probability of 10%, then we can quantify these probabilities for all of these component events. And we have this system events probability distribution that we just quantified. Then we can now we are now ready to make inferences using Bayesian network algorithms. And one of those is variable elimination, which is in which case we decide the order of variable elimination, and we leave only the variable in the Bayesian network graph that whose marginal distribution we are interested in. So for instance, if we are interested in this S, then we eliminate all these components, then until we get only S, so that we can specify the marginal distribution. So for instance, if we specify this elimination order, then this variable elimination, repeat product, and summation to remove a variable from graph. So for instance, here, first, if we want to remove x1, then we multiply x1 with its associated node, which is in the graph. It has the effect of merging these two nodes. And in case of summation, then now we go on to summation, where now we marginalize x1 to remove this particular variable from the graph, and in this way we now have this new graph where x1's uncertainty has been observed to other components, and we repeat this process until we end up until we remove all the specified variables. And now we have this marginal distribution where we can conclude that the failure probability is this much. So, and if you are interested in, for instance, a joint distribution of x1 and s to understand the relevance between this particular component event and the system event, then we can eliminate all component events but x1, and in this way we can make various types of inferences. So to implement this, we have this in MBNpy, we have this inference module where we have this variable elimination, and we provide the CPMs that is a series of the probability distributions that we quantified, and then we specify the variable elimination, and then we can get this new CPM that is the result of eliminating all these specified components in the order. So in this case, we can get this system failure probability being about 0.5%. Then now, all these efforts lead to this natural question that if all this process can be automated for arbitrarily complex systems. And this has been a long question for me as well. So because what happened before was that we used to have this decomposition algorithms for mostly two-terminal network connectivity and maximum growth, where we have one origin and destination pair, and we are interested in connectivity or maximum flow. And all these decomposition methods have been developed to address this particular class of problems. But then now, if there's an arbitrary system definition, and if we can automatically identify this decomposition as well as the minimal rules, then that will that will be highly useful. And this has been a long question for me when I joined Daniel's group in 2022. And now we have this exciting development that that does this that addresses this task. So now we call it this BRC algorithm. So which is also incorporated this MBNpy. So for instance, I'll first show how it works in this toolkit where we need two inputs, the system function and the component probabilities. So first, the system function needs to get this component state as the input as an input, and it needs to return whether it fails or survives. So for instance, in this case, there is this we just came up with this random definition where there are 5 components with different capacities, and the system fails if the total capacity of the surviving components is less than 10. Then, so in that case, return failure, and otherwise the system survives and return survival. These two outputs are optional. So without this, the system, the function can still run. But with but these optional outputs can help accelerating the BRC, which you can find the more detailed descriptions of the tutorial. And then the second input is component probabilities, where we need to specify for each component, for each state, how the probabilities are defined. And this applies to multi-state components, so you can add more states if you have. The only rule is that it starts from 0 and the state is sequential. Then, if you provide them these two inputs, and this is just an optional input because I wanted to print out more of the progresses. Then, if you run this BRC, then now we can get all these branches where the system failure probability is obtained as 23%, and it took around 0.3 seconds because it's relatively a very simple question, and it was completed after 13 system functions, and we found the 7 and 5 minimal survival rules and the 12 branches. So the outputs are first the branches and the rules, which are used for system inferences. So if we look at the rules that identified, then we can find that it found all the combinations that lead to either system survival or failure. So algorithmically, it is this BRC algorithm is a bunch of heuristic strategies that were based on the previous observations with these decomposition methods. So this is a brief illustration where the focus is on how we can find the new rules from these branches that we cannot specify the system state, and also how we can renew the decomposition with new rules. So the idea is that without looking inside the system function, how we can identify these branches and the rules. So what this algorithm does is that it looks at the unspecified branches found, and it is trying to, and it runs a system function on this unknown state, and based on that, it tries to find a new survivor or failure rule, and based on that, it updates a rule, and then using these given rules, it tries to find out the best ordering of decomposition, and after doing that, if there's no unspecified branches, otherwise every branch belongs to either survivor or failure domain, then this means that we can now do the exact inference. So so we exit the algorithm. Otherwise, if there are too many branches that we want to terminate the algorithm, then now we do this approximate inference by either bounding or performing MCS on these unspecified branches only, or otherwise we go back and we continue this process of identifying new rules and the new decomposition, etc. And the output are first the system failure probability, but also the branches and the rule set which we can use for other types of inferences, not only the system failure probability calculation. So then compared with sampling, which is the most common method in this area, the complexity is different because in case of the decomposition method, but I had to mention that BRC algorithm is based on this assumption that a system is coherent. In other words, vector component state do not worsen the system state. And this information on coherency is very powerful, that as we show it later, that how it can significantly reduce the computation. But of course, the challenge lies with these incoherent systems, which is remaining question that we need to address. So then if we compare this complexity, then in case of this decomposition method, that it's like if we identify that this particular sample belongs to a system domain, it's a system failure, that we automatically conclude that the overall state is a system failure. And if we find the survivor sample, then we conclude that the rest of the domain that is better than this state, this system belongs to system failure, as it's the survivor domain. And as we continue this process, then we continue with identify more domains, and we continue this process until we identify enough domains. On the other hand, in sampling cases, because these are point-based exploration, so even if we know about this state, we need to further generate samples in the domains that we could infer from the previous results. And so the complexity here, in case of this decomposition methods, are linear to the number of branches because they decide how many arithmetics we need to perform. And heuristically, this number of branches increases quite rapidly with the number of rules. However, these number of rules, especially with these very complex networks, marginally increases with the number of components. So here, the underlying assumption is that usually, even if a network has a very high dimension at the first level, usually the underlying complexity, which is the number of rules, is much less than what we see in the apparent level. Other case, on the other hand, these sampling methods, they usually have this difficulty with decreasing failure probability. So now we can see that their complexity is affected by different factors, so they have quite complementary characteristics, because in case of this systems with a very low probability, it is usually the case that the underlying rules are simple, that they have so few failure rules that cover the failure domain. So usually the complexity is much less than is much easier, which but on the other hand, for these systems with high probability, then for sampling, they are really easy to estimate this value. But that also means that the system has a lot of survivor and failure rules that are comparable to each other. In that case, the complexity is usually quite high for decomposition methods. So they have quite different characteristics in which problems they feel difficulty. So then, of course, for these analytical methods, the problem is always that when they hit the ceiling, then that's the game over. We cannot go on, because now we are seeing this exponential, this numerous branches, and we cannot go on branch. And in that case, even if we go on decomposition, we usually end up specifying very small fractional probability with lots more branches. So at some point, we need to stop. And in that case, what we end up is first, we have these failure branches with whose sum of probabilities leads to system the failure probability, and also a bunch of survivor branches whose sum leads to system survivor probability. And also we have these unknown branches where the upper bound has system survival and the lower bound has system failure. So we don't know we don't know which probability they belong to, and we have, but always these branches, the sum of these branches probability should be 1. Then we can do 2 different approximate inference here. First, we can do deterministic bounding, in which case the lower bound is the failure probability, the failure branch's probability, and the upper bound is 1 minus survival probability, or the failure probability plus the unknown probability. And we can terminate the algorithm if this unknown branch's probability is less than the failure 5% of the failure probability domain, which means that we have this very narrow bounding bound that is in regard to the failure probability. Otherwise, and usually this works because what we end up having is that a few branches explain most of the system domain, and in the end, we end up with this very fractional branches that don't take up much space, much probability, but their number is huge that we cannot exhaustively identify. And or we can also perform NCS on these unspecified branches, in which case this is preferred when this bound is quite huge that we cannot conclude, we cannot have this enough accuracy. In this case, this coefficient of variance reduces to this amount, which is always positive, and if this probability of this unknown branch is comparable to the number of to the failure probability, then we can have this significant buffer to reduce the COV than just a straightforward MCS. Then now the question is how consistently this BRC algorithm works for different types of systems and complexity. So to test this, we analyze this EMA highway benchmark network with 74 nodes and 139 edges, and we set this 139 edges as a component event. And we came up with this new definition of a system failure by reflecting the emergency activities, where we want to decide from an origin if it takes more than twice the usual time to any of these closure airports, which are represented by these 2 nodes. So then this means that there are 74 nodes minus 2 airports. So now we have 72 nodes, which each of which constitutes a system event, and we compare this 72 event. We analyze this 72 event to analyze how consistently this method can work. And we terminated we performed approximate inference. So we terminated the algorithm by when we reach this 5% of bound with regard to the lower bound, or if we have more than 50,000 branches, in which case we perform the NCS on these unspecified branches. And so this is the result where we mapped out the failure probability for each of these origins, and with this assumed epicenter location. And this blue bar shows the computational time for the branch of BRC, and the yellow bar shows the computation for NCS, and considering the y-axis in log scale, because significantly reduce the computation time. And another advantage of this branching bound, especially compared to sampling, is that we can rapidly update the probability. And this is because in case of sampling, when the component probabilities change, then the representativeness of the samples are lost. So we need another sampling. On the other hand, while this BRC algorithm takes a lot of time for decomposition, but once this decomposition is done, even if when the probabilities change, then we don't have to do all the decomposition again, but rather we can simply replace the probabilities and repeat the arithmetic that we mapped out before. So decomposition enables this pre-processing concept, and therefore this real time over large scale systems. And we test this on our method, where we have this, we assume this new earthquake scenario, and this red bar show how much it took for this for update, and again the y-axis in room scale. And it took about 10 minutes, while it previously took about around a day. And when we consider that there are 72 events, then it took less than 10 seconds per system for update. And because we are performing approximate inference, now we had to check if this does not exacerbate the bounding. And surprisingly, in both cases, it was well contained. So in case of these 62 nodes where 62 system events that we performed deterministic bounding, the bounds were well contained, and in many cases it was even reduced. And also surprisingly, in case of where we performed this MCS, because of the presence of this buffer term, even if the component probability change and the COV by MCS samples changed, but still we could get good enough COV. So in summary, this presentation was about how we can use Bayesian network to handle these large-scale complex networks or systems, and we can use this BRC to automatically encode the system probability distribution, while MBN can be used to store these probabilities and perform various inferences. But still, there are lots of a long way to go to address these complex large-scale systems in a practical manner. And first of all, the decomposition by BRC algorithm can take very long. So now we are under this investigation where we can transform these logic-based operations on tensor-based operations by reformulating the problem in terms of tensor-based tests. And in that way, we can use GPU programming, or even more exploratively quantum computing, if we successfully manage to formulate this problem as a purely mathematical problems that are represented by these tensors. And of course, there's these incoherent systems that are still conundrum in this area. And incoherence happens when users have conflicting interests to the systems optimization, as in traffic simulation, or if there is an error in operation because of some insufficient information. So for instance, in power grid, if the substation is not aware of the failures in the downstream and they send the electricity, then there will be this tripping and cascading failure. In that case, if it would be better if this upstream was failed, then this creates this incoherence in the system. But the part that the fact we are focusing on is that usually these systems are generally coherent, but there is some incoherency by this particularity in their operation. And if we can cleverly use this local characteristics, then we should be able to tackle this one, although it is still an open question. And most important, this network reliability is yet to penetrate the practice. And we have many challenging applications like cascading rate delays, wildfire evacuation, and cascading power grid failures, as we just seen in Spain early this year. And for these problems, there isn't even consensus on how we need to define these networks, how we need to mathematically simulate these systems. It's still an open question. And so there is lots of it's a long way to go that we really achieve a resilient infrastructure. And thank you for listening.